We're now going to have a look at probability theory. This is about quantifying likelihood using numbers. So far, we've just been working with an abstract idea of a state space, of events, and set theoretic operations like partitions of a state space. Well, now we're going to translate this into numbers and develop the ideas of probability theory. Now, I expect many of you will have seen probability theory before, in particular advanced statistics in year one, although I suspect that might feel like quite a long time ago now, so it's worth going over probability again. In particular, we're going to work with the idea of a probability measure. Now, you may be used to thinking of probabilities essentially as non-negative numbers that add up to 1. Okay, this would be how you've encountered probability when you did game theory and so on in microeconomics. Really, however, the more widely accepted approach to studying probability is to work with what are called probability measures. Okay, so this is an axiomatic definition of probability, and a probability measure is going to be a function rather than just a collection of numbers. It's going to be a function that turns an event into a number, and we'll interpret that number as the event's likelihood. So let's look at the axioms of probability. Indeed, these axioms were developed in the first half of the 20th century. So while probability has been around for a long time, the modern way of looking at probability is not that old. So we're going to take capital S to be the set of states and let omega be the set of events. So if we're talking about a finite set of states, we can just let omega be the set of all possible subsets. A probability measure is a function, and it's going to take events, so elements from omega, and turn them into numbers. Okay, that's the first idea. Probabilities measures are functions. We plug events into the function and out pops a number. And these functions, these probability measures, must satisfy 3 rules in order to be called probability measures. These were first described by Kolmogorov. Excuse my pronunciation. So the first rule is that when we plug any event into the probability measure, the number that pops out is never less than 0. So it's always non-negative for all events in omega. The second is a normalization, which is not really needed, but it's a convention that we keep, that if we take the probability of the entire state space, so the probability that something happens, I suppose, then that is simply equal to 1. Okay, so this is a normalization. A different number could have been chosen, but we take probability 1 to be absolute certainty. The third condition, sometimes called the additivity property, is the following. If we take any 2 events, A and B, and these events are disjoint, by which I mean they have an empty intersection, so they don't have any elements in common. For example, the odd numbers and the even numbers would be 2 disjoint events. They don't have any element in common. In that case, if we want to describe the probability of A or B, so A union B can be read A or B, the probability that one of these happens, then we can sum up the individual probabilities. The probability of A or B, where A and B are disjoint, is equal to the probability of A plus the probability of B. Okay, so any function that satisfies these 3 rules is a probability measure on the set of events. Okay, so there are infinitely many different types of these functions. This is going to be useful later on, where we'll talk about subjective expected utility theory. So you could imagine probabilities describing individuals' beliefs about certain things happening. And of course, different decision makers may well have different beliefs about different events and their likelihoods. So each individual would have a different probability measure over the same set of states. As an exercise, and to get used to working with the axiomatic definition of probability, it's worth going through the following. So show that for any event in omega, so for all A belonging to omega, we have the following property, that the probability of not A, the probability of the complement of A, is equal to 1 minus the probability of A. Okay, so I've put some hints on the screen for you, which you can use to prove this. So the first hint is that, well, if we take any event and we take the union of A and not A, then that's the whole state space. So all of the states that are in A, union with all of the states that are not in A, that is all of the possible states. Okay, so A union not A is equal to the state space S. And also for all A in omega, so for all events, we have that if we look at the intersection of A and not A, so the intersection of all of the states that belong to event A with the set of all states that are not in A, then this intersection is empty. Okay, so A intersect with not A is an empty set. So there's some hints. Pause the tape and have a quick go at proving the required equation above in this exercise. Now that we know what we mean by probability measures as functions that satisfy certain rules. The Kolmogorov axioms, we labeled them 1, 2, and 3, non-negativity, the normalization condition, and the disjoint additivity property. Let's now talk about conditional probability, and we'll reach Bayes' rule by the end of this. This is going to be crucial for discussing the idea of probabilities changing in response to new information, and information is our big topic here. So what do we mean by conditional probability? I've written P, so the probability of A and then a vertical line with B on the other side. You should read that notation as the probability of event A given event B. Okay, so it's what's the probability of A given the information that event B is true or has happened. Another way of reading this is simply to say the probability of A conditional on B. Okay, now provided that the probability of B is not 0, so as long as the probability of B is positive, we can define the conditional probability P of A given B as following. The probability of A given B is equal to the probability of A and B, so A intersection with B, divided by the probability of B. Okay, now because we're dividing there, that's why we need the probability of B to be non-zero. If the probability of B is 0, then this conditional probability is not defined. Notice that this is a definition of what we mean by a conditional probability. So when we write P of A given B, what we mean is that it's the same as the probability of A intersected with B divided by the probability of B. So this is not an equation that we need to prove. It's a definition that we're going to work with. So here's an exercise you can do to get to grips with working with this definition of conditional probability. So let's let the probability of some event B be strictly greater than 0. So we can define a conditional probability for any event A given B. Now let's define a function P subscript B. Okay, now this function is defined so that for all events A, P subscript B of A is equal to the conditional probability of A given B. The exercise now is to show that this function P subscript B is indeed a probability measure if we restrict the set of states to be just B. Okay, now when I say restrict the set of states to be B, one way of thinking about this is just to say, well, the probability of B using this new measure P subscript B, we would hope that that's equal to 1. So I've included that as a hint when you're going to show that the second of the probability axioms is satisfied. We're going to interpret that as showing that P subscript B of the event B is equal to 1. I've given another hint below, which is just a fact about basic set theory operations, about intersections and unions, which is the following. If we take any two events, A and C, and we take their union, A union C, and then intersect that union with the event B, this is the same as taking each event A and C individually, intersecting them with B, and then taking the union of those separate intersections. So that would be one useful trick as you show that the additivity property still holds, the disjoint additivity property holds for this function P subscript B, and that the conditional probability as we define it, really does induce a probability measure on a restricted set of states. So pause the tape now and have a go at that exercise before continuing. Now that we've defined conditional probability, we can derive a rule of probability calculus called the general multiplication rule. Indeed, sometimes this general multiplication rule is given as an axiom, and from this rule you can derive the definition of conditional probability. That was how De Finetti preferred to do it, but Kolmogorov did it the way that we're doing things. We've got our definition of conditional probability, so let's derive this idea of the general multiplication rule. Now, a very basic result in set theory is that if we take the intersection of two sets, it doesn't matter which order that we do this. So if I take the intersection of A and B, or if I intersect B with A, I get the same result. Formally, we describe intersection as being a commutative property, very similar to addition. So 1 plus 2 is exactly the same as 2 plus 1. So we know that the order of this intersection doesn't matter, which means if we were to find the probability of these intersections, so if we had a probability measure P and we plugged in the intersection of A with B, or we plugged in the intersection of B with A, the same number should pop out because they are the same sets. So let's consider two sets, A and B, two events, which both have strictly positive probability according to the probability measure P. Now we know how to define these conditional probabilities, the conditional probability of A given B, and the conditional probability of B given A. So we know how to define both of these, and just notice that on the numerator of each of these fractions, the intersection of A and B, the probability of that event is being assessed. And of course, we know that these are equal to each other. So from this, we can very quickly rearrange and derive the general multiplication rule, which is the following. The probability of two events, so the intersection of A and B, or simply the probability of A and B, is equal to the probability of A multiplied by the probability of B conditional on A. Alternatively, we could reverse the order and say that the probability of A and B is equal to the probability of B multiplied by the probability of A conditional on B. Let's go on paper now and work a bit more with this, and from here we'll talk about Bayes' rule and Bayesian updating of probabilities. Okay, so now we've established the general multiplication rule, we're going to talk about Bayesian updating, Bayes' rule and Bayesian updating. So if we remember, the general multiplication rule says that the probability of A and B can be expressed in two ways. We can calculate this in two equivalent ways. We can take the probability of A and multiply it by the probability of B conditional on A. Or we could do it in the reverse order. Imagine that B happens first, probability B, and then given that B has happened, what's the probability that A happens? A conditional on B. Okay, so this is the general multiplication rule for probabilities and conditional probabilities. Now, let me just mention quickly one idea that you may have heard of before, the idea of statistical independence. Intuitively, the idea of independence means that, one event has no influence on another event. Okay, so they are independent. What do we mean by that? Well, if I say that the probability of A is equal to the probability of A conditional on B, okay? So what does this mean? When I find out that B has happened, the probability of A is exactly the same as it was in the first place, okay? So we would say A and B, events A and B, are statistically independent if this equation is true, in which case we get the nice expression that the probability of A and B, if two events are statistically independent, I just multiply their probabilities, PA multiplied by PB. Okay? So it would be PB multiplied by PA given PB, PA given B, which is the same as PA. Okay, so this is where you get that. You've probably heard the way of remembering how to work with probabilities, that when you say or, you add, and when you say and, you multiply. We can be a little bit more specific and say, when we say or, so one event or another, if those events are disjoint, then we add. When we say and, so intersection, if those events are statistically independent, then we can multiply their probabilities. Okay, and that comes from the general multiplication rule, which was just built by using the definition of conditional probability. Okay, so what is Bayes' rule? Let's just jump straight to this. And really, we're just going to rewrite the conditional probability in terms of say the conditional probability of A given B can be found by calculating. So I'm just going to rearrange these terms. So I would get the probability of A multiplied by the probability of B given A, and then divided by the probability of B. Okay, so expressed this way, it's this relationship is often called Bayes' rule. Okay, so why is this important? Well, it establishes a connection between beliefs after we receive information and before we receive information. So sometimes the probability of A, just expressed as an unconditional probability, is called a prior. So it's my prior belief, prior to receiving any new information, my belief quantifying the likelihood that event A will happen is given by the number PA. Once I receive information that event B has happened, my belief changes to A given B, and sometimes we call this the posterior belief or the posterior probability, or sometimes it's just called the updated or revised probability. Okay, and we call this process Bayesian updating. Okay, so when I'm making decisions, I have some belief that A will happen, which is quantified by this probability measure P. I assign the number P of A to the likelihood that A will happen. If I receive new information, if I receive information that event B has obtained, then I have to condition on the fact that I now know that B has happened. So my belief regarding event A is the probability of A conditional on B. And I can calculate using this term, okay? So I need to know the probability of B and the probability of B given A. Sometimes this term is called the precision term, okay? Okay, so that's a basic version of Bayes' rule. There's another nice way we can express this. It's a little hard to read, but it's quite easy to write. So I'd encourage you to practice writing it yourself. So far we have that the probability of A given B, so my posterior probability takes my prior belief and then multiplies it by P B given A divided by PB. Okay. So I may know these terms. I may know enough now to calculate my updated probability, but very often we don't have all these pieces of information. Okay. So one nice trick, which you'll need as you solve the exercise classes, is to think about this probability of B a little more. Okay. So here's the nice trick. Think about how B could happen. Okay. Now, it may be disjoint from A and it might not be. So I could say, well, sometimes B happens with some probability. B happens at the same time as A. Okay, so B intersects with A. Sometimes that happens. And sometimes B intersects with not A. Okay, so this line here is just saying, well, what's all the different ways that this event B can happen? It happens when A happens, or, so I'm adding, it happens when A doesn't happen, okay? So already I've broken this down. I might not know PB, but maybe I know these two terms, okay? Now we can say a bit more about these because from the general multiplication rule, we know how to calculate these intersections, okay? So how would I calculate the probability of B intersecting with A? I could do it in several ways. For instance, I could say it's the probability of A multiplied by the probability of B conditional on A, okay? And there are other ways I could have written that as well, okay? If I think it could have written probability of B multiplied by the probability of A conditional on B, okay? So knowing that you can write these things in different ways using that general multiplication rule could be very useful. And I can do the same trick here. I could say, well, the probability of not A, okay, which we've already proved earlier in the lecture is 1 minus the probability of A, and then multiply by the probability of B conditioning on not A, okay? So I might not know this, but if I know the probability of A, that's the thing we're updating, so presumably I do know it. And then I just need to know this precision term. The probability of not A can be calculated as 1 minus this, and then I need to know this precision term here, okay? So this is a very useful way of breaking down this probability of B into things that we might know, okay? And to give you a clue, I'm going to give you questions in the exercise class where you don't know this, but you will know enough about these different parts to be able to calculate it. So let's just rewrite Bayes' rule now as saying, well, if I want to update my probability, okay, form my posterior probability, the probability of A conditional on B, I take the probability I started with, my prior belief, then I multiply it by the conditional B conditional on A, that what we called a precision term, and then I can divide by this whole mess at the bottom, okay? Now my experience from teaching this is that it's kind of confusing to watch because I'm writing lots of different A's and B's and conditioning, but if you write it yourself, if you practice writing it and saying it aloud as you do it, and get over the embarrassment of doing that, you'll find it much easier to write than to read. Okay, so take this idea, you will need to use it in the exercise class. So that covers our topics for Lecture 1 of Advanced Microeconomics. Today we've looked at information, modeling uncertainty. Information is a reduction in uncertainty, so we looked at how to model uncertainty using a state space. We talked about partitions of this state space as a way of modeling information structures and interpreting the elements of that partition as information sets. We also talked about comparing information structures by using the idea of one information structure being a finer partition of the state space than another information partition. And then we covered some elements of probability theory and conditional probability, the general multiplication rule, and Bayesian updating. In the next lecture, we're going to be covering expected utility theory. This is the most important model for choice under risk in economics. Choice under risk and uncertainty. We'll distinguish between these next week, and we'll cover the great axiomatic foundation of expected utility provided by John von Neumann and Oscar Morgenstern in their revolutionary book, The Theory of Games and Economic Behavior. So loads to look forward to. I look forward to seeing you next time. In the meantime, take care.